Welcome to another video. This week we're looking at the methods for doing statistical inference with proportions. So you use these methods when you have categorical data instead of numerical data, and it lets you decide like what the true population proportion of people who gave a certain answer is. So this is a simple example of a hypothesis testing situation where we have someone who wants to prove that they're psychic. Researchers in psychology developed these 5 cards here called Zener cards that you can use to test to see if somebody has psychic powers. So the way the test works is you have a tester who's going to look at a card randomly selected and visualize what they're seeing in their head, and then you have a subject who's going to try to prove that they're psychic by using their psychic powers to read the mind of the tester and see what card the tester is looking at. And then they say what they think the card is, and you record whether they got it right or wrong, and then you repeat lots of times. And I actually took this test when I was 14. My cousin and I were testing each other to see if we were psychic, and it turns out I did really well. I got 10 out of 25 right. And so we'll come back to that and see if that's evidence that maybe I'm psychic. But let's get started with the questions here. So first of all, if somebody is not psychic and they're just guessing, then what percent of time would they get the right answer on average? So looking at these 5 cards, if you're just guessing, you're going to either guess, oh, I think it's a star, or I think it's a wavy squiggly lines thing. And how often are you going to be right? Well, since it's just a guess and there's 5 possible choices, I'll let you think about that for a second. What's the probability they're going to guess right? Well, it's 1 out of 5, right? So that's the probability they're going to be right. So let's just write that down. All right, so the probability that they're right if they're just guessing is 1 out of 5, which is the same as 20% or the same as 0.20. I really don't care which way you write this answer. All of these are correct. Okay, the next question is there are 2 possible hypotheses in this situation. Either the subject really is psychic or they're just guessing. Which of the 2 hypotheses is the null hypothesis? So let me write down what null hypotheses look like when you're testing about proportions. So the null hypothesis, the H0, is always going to be that the true proportion P, that's the symbol you use, so the symbol P, is no different than, is equal to a certain number. And so saying that P is no different than a number, we need a number here, and one number is that it's just, what they're getting, the results are just chance. No different than chance makes a good null hypothesis. We use that a lot. And if it's no different than chance, then it's no different than a 20% chance. So there's a specific number. And remember, a null hypothesis has to be a specific claim about a population parameter. So that's exactly what this is. We have a population parameter, P, that we don't know. That's how often the person will be right. It's basically a measure of how strong their psychic powers are. And the null hypothesis says it's no different than just dumb luck guessing, 0.2. So that's saying that they're not psychic. All right, so the null hypothesis is the hypothesis that they're just guessing. And then the alternative is the hypothesis that actually, no, maybe there actually is something going on here. So maybe they really are psychic. And if they're really psychic, then I guess they're going to be right more than 20% of the time. So maybe they're only a little bit psychic, and their psychic powers aren't perfect, but it's going to be more than 20 because they're a little bit psychic. Okay, so those are our 2 hypotheses in this situation. Why does it make sense to do a one-sided alternative hypothesis here? Well, if we don't know what P is, and we're not sure if it's equal to 20, it's either going to be 20 because they're just guessing, or it's going to be that they're really psychic. And if they're really psychic, which way is it going to tilt? Well, if they're psychic, they're going to be right more than 20% of the time. I don't think we need to worry about people who are like anti-psychic, who have the incredible ability to guess wrong more than chance. So I don't think we need to worry about the other direction the inequality could go. So we don't need to do a 2-sided alternative hypothesis here. Okay, so it's because they are either psychic or just guessing. And if they're psychic, then they're better than 20% chance, not worse. Okay, so now when I did this, I got 10 out of 25 correct. So this is something that my cousin and I did, like I said, we were testing each other. and wow, I was psychic. Okay, so here's what my p hat was. Remember, the sample proportion is the proportion you get from a sample. We use a symbol p hat to distinguish it from the p without a hat, which is the population proportion. So we put the little hat on top of it to say this came from sample data. And I was right 10 times 10 successes out of 25 total, so that's 40% success rate. And that's pretty good. That's way better than the null hypothesis. So it looks like maybe there's something going on here. So let's test that. And that's what this formula for a hypothesis test does. It tells us if our sample data is far enough away from what the null hypothesis said the p should have been to be statistically significant evidence that there's something going on. So we got to calculate the z-value first. So we're going to find out what z is equal to. And to do this, I recommend using the online formula sheet, the interactive formula sheet. So let me pull that up. It's on our class website, software, interactive formulas. Just click on that. And here are the 4 different formulas for doing inference about proportions. So last week we were talking about the 4 formulas for t-tests and t-confidence intervals when you were talking about averages of a quantitative variable. This week we're going to be talking about proportions of a categorical variable, like were you right or wrong. And in this case, the formula I want is this one. It's the one sample z-value that lets you do a hypothesis test. Okay, I've got all the numbers I need. My p hat was 40%. The p0, the null hypothesis, said that I should have only been right about 20% of the time. And there were 25 tries. There were 25 times when my cousin held up a card and I read his mind and said what it was. And so my z-value is 2.5. And so let me write that down. Z is 2.5. And if you remember what a bell curve looks like, what we have here is a bell curve, and I'm 2.5 standard deviations above average. In fact, let me really quickly draw a bell curve here. So I've got, oh God, that's terrible. So I don't know if this is going to work, but here's a line, and I've got a bell curve. And so what the bell curve looks like is it goes up in the middle, and then it comes back down, and the middle here is right at a z-value of 0, and I'm not 1, I'm not 2, I'm 2.5 standard deviations above where you would have expected. And so the p-value is going to be the part of the bell curve here that is more extreme, as extreme or more than what I got. And so that's what I need to find now, is what part of the bell curve, what probability would there be that somebody would do even better than I did if they were doing this test. And so that's going to be the p-value, and we know how to do that too. We've been doing that since the very beginning of the course. You can just go back to the bell curve slider on my website, or you can use the app on your phone. Here I've got a middle of 0 and a standard deviation of 1 because I'm talking about standard z-values. And then I have my x is 2.5, and I want the proportion above x, so I want the right tail here. And that has a chance of happening at 0.006, which if I move the decimal place 2 places, that's going to be 0.6%. So my p-value, p equals 0.6%. And so I found the z-value, then I found the corresponding p-value. Now, is the evidence of the test statistically significant evidence here? And the answer actually is yeah. Wow, that's really significant, right? That's way below 5%. It's even below 1%. So this is what we might say would be very significant evidence. So yes, it is very significant. So that's great. I'm psychic. That's amazing. You probably didn't know that about me. But actually, there's a couple problems here. The first problem is that you'll notice the sample size is only 25. That's a pretty small sample. And if the null hypothesis is true, and I'm just guessing, then you would have expected me to get about 5 right anyway. And the fact that I got 10 right, that's only 5 more than you would have expected. So already the sample size is small, so that makes this a little bit fishy. And there's another much bigger problem, which I didn't share in this workshop, so you wouldn't have known it. But the data here was actually not well collected. This was me as a 14-year-old kid, and I really wanted to be psychic. Like, I thought that would be the coolest thing if I was psychic. So what did I do? I got these, I found this book about psychic powers. I learned about Zener cards. I made a couple of these with index cards, and then I told my cousin, you got to test me. And the first time we tested me, I didn't have psychic powers. And the second time and the third time. And finally, something like the fifth or the sixth time we were doing the test, I got a result. And in the book, it said if you got like 9 or more, then you were psychic. And I got 10 right. And so, like, on the fifth or sixth try, I managed to prove that I was psychic. But that's not how hypothesis testing works. If you keep testing over and over and over again until you get the p-value that you want, until you get something that looks significant, then what you're doing is just garbage. In fact, this is something that's sometimes known as p-hacking, right? You keep doing experiments until you get a p-value that looks good. If you do that, then it's completely useless, because eventually you're going to get a p-value that's pretty low just by dumb luck. And it doesn't mean that there's anything significant going on. It just means that you kept cheating until you got something that looked good. So always be very careful. Make sure that when you're reading a statistical study, you find out what they did. If they really did 20 different studies and then they're only telling you about the one that looks significant, then that is not really good science. As always, if you have any questions about this, hopefully this new formula is pretty straightforward to use. But when you're doing the homework or when you're trying some of these other workshops, let me know if you have questions, and I'll talk to you guys later.